Okay, so now we are into the theory of what multidimensional integrals are. And we're going to start with this warm-up. Let f of x equals x squared. What is the Riemann sum of f over 0, 1 using 5 terms? So let me just sketch what's going on here. That's the y-axis. This is the x-axis. And we're going to break the interval up. This is 1. We're going to break it up into 5 pieces. 1, 2, 3, 4, 5. Break it up into 5 pieces, each one a distance of 0.4. I'm sorry, 0.2. Okay, and then we have a graph of the function y is equal to x squared. Wow. We have the graph of this function, y is equal to x squared, and then the Riemann sums say do something like this. This would be, if you remember, this is the right hand Riemann sum. I have a Desmos graph that we'll look at in just a minute. Okay, and so the Riemann sum then is going to be the sum from k is equal to 1 to k is equal to 5, f of, so remember it's going to be k times delta x, which in this case is 0.2. Actually, let me write this as 0.2k. It might look a little nicer. Okay, that's the height of each one of these rectangles. So when k is equal to 1, 0.2 times k is 0.2. When k is equal to 2, 0.2 times k is equal to 0.2. When k is equal to 3, this is what it is. When k is equal to 4, 0.2 times k is 0.8. And when k is equal to 5, 0.2 times k is 1. And now we multiply by the width of each one of these rectangles. The width of each one of these rectangles is 0.2. Or we would call this delta x. Okay, or in general, well, not in general, let's just look at this for now. Now let me get up the Desmos so we can look at it a little better. So this is just the Riemann sum. This is the graph y equals x squared. The green part are the Riemann sums. These are using left endpoints. If you want the picture to look like what we just did, we could use right endpoints like this. And then the sum of these rectangles is an estimate of the area under the curve y is equal to x squared. And this is what we would get if we used midpoints. Okay, this is just a refresher of what you've already seen from Calc 1. Now I want to look at an example that you might not have seen in Calc 1, but is similar to the problems that we've done so far. So we have, so the typesetting got a little messed up. So we have a string of length 1. I'm just going to kind of make it a fixed string like this that goes from x is equal to 0 to x is equal to 1, and it has this weight density, delta of x is equal to 1 plus x. Okay, so what is the weight of this string? We want to sketch a picture that depicts this. So we're going to look at a Riemann sum. So again, we're going to divide this into 5 equal pieces, every 0.2 feet. Okay, and then the weight is going to be approximately equal to, well, we'll just treat the weight as being constant on each one of these squares. Okay, so the weight of this square is going to be 1 plus 0.2 times its distance, times its length. So 1 plus 0.2 pounds per feet times 0.2 feet. That's the mass of this rectangle or this part of the string. Next part of the string, again, we're going to just treat its weight to be constant over this portion, and we'll say that, or the weight density is constant over this portion, and the weight density is equal to 1 plus x, where x is equal to 0.4. So this is going to be 1 plus 0.4 times the length of that interval, which is 0.2. This is pounds per feet. This is feet, so similar units here, or same units here. So these are pound units, which is what we want. And now approximately the weight of this section right here is going to be 1 plus 0.6 times 0.2. Again, we're treating the mass density as being constant on this portion right here at 0.6. Sorry, my son wanted to show me something. Then the next term is going to be 1 plus 0.8 times 0.2. Again, that is approximately the weight of this segment of the string, and then plus 1 plus 1 times 0.2. And again, that's approximately the weight of this string. Okay, so the weight density of this string is variable. It's 1 plus x pounds per feet. But in doing the Riemann sums, we're treating it as being constant on each one of these pieces and saying that it's equal to the density function evaluated at the right endpoint. And we could get a similar estimation if we had said it was constant on this interval, but evaluated at the left endpoint instead of the right endpoint. They're both similar. Okay, so these are two different ways to get a Riemann sum to estimate, say, the area under the curve or the weight of a string. And remember, the idea is we take these divisions, we make smaller and smaller divisions. We make these divisions get smaller and smaller and smaller, so we get more and more subintervals with smaller and smaller length. And the limit, as the number of subintervals goes to infinity and their length goes to 0, this we call the integral of a function. And it will give you either the area under the curve in this example, or it will give you the weight of the string in this example, or there's other physical interpretations. So if you have definitely seen these things before, maybe not the string, but you've definitely seen the first example. If it's something that you are having trouble remember, go back and try to read the textbook some, because it's going to be something that this class is going to use. It's a concept that you need to understand before we can go to multiple integrals.